So let's see if we can bring all this complex number stuff back into the differential equation that we were trying to solve. So remember we had this second order linear homogeneous differential equation with constant coefficients. We wrote down the characteristic equation by replacing y double prime with r squared, y prime with r, and y with constant 1 basically. And then we had complex roots when we used the quadratic formula, which is fine. You can take the roots and put them into our general solution, and this is valid. The only problem was this was a complex solution, and if we were dealing with something like one-dimensional motion or something like that, in real life we would want a real valued function for y. We would expect that. So we do have a tool now. Our tool is e to the I theta equals cosine theta plus I sine theta. That's the beautiful Euler's identity. Okay, so let's break this up into parts that cause problems and parts that don't. So this is a, e. There's a negative 2t there. That's fine. And then in the exponent, it would be plus 3it. So that's the same as multiplying by another e to the 3it. It's just using exponent rules. And this is plus b, e to the negative 2t, e to the negative 3it. And now, these ugly parts with the i's, we can use Euler's identity to change into something that will eventually be better. Okay, so using Euler's identity, e to the 3it is cosine of 3t, so theta is 3t, plus I sine of 3t. And then we get over here plus b e to the negative 2t, and this is cosine of negative 3t, plus I sine of negative 3t. Normally I'm not a huge fan of doing more writing, but let's just write out one more line and fix that big second term. So we'll write the first term as is, plus I sine of 3t, and then plus b times e to the negative 2t, and then cosine of negative 3t is the same as cosine of positive 3t. And then sine of negative 3t is the same as negative sine of positive 3t. If you can't remember that, I always just draw a little unit circle. Here's my angle 3t, here's negative 3t, other direction. The x-coordinates are the same, both the same sign, and the y-coordinates are the same value but opposite sign. The y-coordinate is sine, x-coordinate is cosine. Great. Now we're going to collect real and complex parts. So let's see, the real parts, and don't forget these factors out front, but the real parts have cosine in them. And they both have an e to the negative 2t. One of them has an a and one of them has a b. So this is a plus b, e to the negative 2t, cosine of 3t. That's the real part of this. And then the rest are the imaginary parts. Same thing. They both have sine 3t. They both have e to the negative 2t, and they both have I. This is going to be a minus b. So this is going to be plus a minus b. There's an I somewhere. The order of this doesn't necessarily matter. E to the negative 2t sine of 3t. So multiplication, you can multiply in any order you want. Okay, great. Now, we're going to do a trick. We're going to set c equal to a plus b. If a and b are just any constants, and actually a and b can be complex, we're just going to set a plus b to be c, and a minus b I to be d. And then c and d will depend on a and b. But actually, since this is a system of two equations, two variables, if you think of the variables as a and b, we could solve for a and b and have a and b depend on c and d. So we could put in any value we want for c and d, and then we would be able to figure out what a and b are. So that makes this look better. So instead of a plus b, we have c, e to the minus 2t, cosine of 3t, plus, and instead of a minus b I, we have d, e to the negative 2t, sine of 3t. And what's nice about this is that nothing is forced to be complex anymore. If we want to keep it real, we just keep c and d real. T is always going to be real because it's time. And then we might go back to this and have a and b be complex. We can solve for a and b once we plug in values of c and d, and that's fine. A and B can be complex here, but we're going to look at our real equation. If you're suspicious of this step, let's just check. So as long as the solutions, since this is homogeneous, right? So we can take any linear combination of existing solutions. So as long as this solution and this solution satisfy the differential equation, then we're convinced that this whole thing does. So we're just going to check the solutions. Y equals e to the negative 2t cosine of 3t, and y equals e to the negative 2t sine of 3t. Doing both is a lot of algebra, so I will show one of them, just so that you're convinced. So we got to take a derivative. We got to use the product rule, unfortunately. So derivative of the first thing is negative 2 e to the negative 2t cosine of 3t. I'm taking derivatives so I can plug it back into the original equation. And then plus e to the negative 2t and the derivative of this, which is negative 3 sine of 3t. So everything's negative right now. Sine of 3t. And then another derivative, which unfortunately we got to do product rule on both of these. So derivative of this again is going to be 4e to the negative 2t cosine of 3t. And then we'll take derivative of this part. There's going to be a negative 3 sine of 3t. So that's a total of positive 6 e to the negative 2t sine of 3t. And then we'll take derivative of this part. So we're going to get another positive 6 e to the negative 2t sine of 3t. And then derivative of sine 3t is positive 3 cosine of 3t. So this sign stays negative. 3 times 3 is 9 e to the negative 2t cosine of 3t. And we should be able to combine this into two terms. So y double prime is actually, let's see, we have 4 e to the negative 2t cosine 3t minus 9 e to the negative 2t cosine 3t. So a total of minus 5 of that term. And then a total of plus 12 of this other term. Okay, let's just see if this works. So the left-hand side of my original differential equation, we're going back to here, is y double prime plus 4y prime plus 13y. Let's just plug these in and see if everything cancels out and we get 0. So we get negative 5 e to the negative 2t cosine of 3t plus 12 e to the negative 2t sine of 3t. And then we're going to add 4 times the first derivative. So minus 2 times 4 is minus 8 e to the negative 2t cosine of 3t. Plus 4 times negative 3 is minus 12 e to the negative 2t sine of 3t. That's that term. And then we're going to add 13 times the original. And the original was just this. So plus 13 e to the negative 2t cosine of 3t. Let's see what happens. For the cosine ones, all of them have e to the negative 2t. So we get negative 5 minus 8 plus 13. That is 0. And then for the sine ones, we get a plus 12 and a negative 12. So that's also 0. So this does equal 0, which works, which equals the right-hand side. So that's good. So this solution satisfies this initial differential equation. If you're still suspicious, check this other one too, and then you should be convinced that this whole thing works.